to Weinberg soon, and he's going to join CITA as an SRA in the fall, for those who don't know yet. So yeah, we're all looking forward to that. And he'll be telling us about inflation, how you make that good for observation.
Thanks. So as Jens said, I'm going to talk about inflation, and specifically what are these pictures shown here have to do with inflation, or to turn things around, how we take pictures like this and learn something about inflation, learn about the earliest periods of our universe that we can understand. So here's a quick outline of my talk. I'm going to start with kind of a lightning review of what inflation is and the observations that we use to study it. And then I'm going to go on and talk about some of the technical aspects dealing with the conservation of correlation functions. And this is going to be split up into a couple of sections here. The first section deals with the conservation of correlation functions during and after local thermal equilibrium. This is based on a paper that should be coming out soon, and that was mostly done. The next one deals with loop corrections, specifically quantum loop corrections during inflation. And this is work in progress, so unfortunately this section will kind of leave you hanging a little bit, but hopefully I can still add some new discussion there. And then lastly, I'll move on and talk about some specific class of multi-field inflationary models and how this story, I'll tell you in the first half, has an impact on the outcome of any of the models on multi-field inflation and a model calculus. So, as I'm sure a lot of you are familiar with, inflation is the accelerated expansion of space that took place in the early universe, or we think took place in the early universe. And for those of us who work in the field, I think it's easy to lose a sense of the scale of inflation. So, just to give you some realistic numbers and some realistic visualization of this, in the time that it took, well, about 1 billionth of the time it takes light to cross an atomic nucleus, patch of space about the size of an atomic nucleus expanded to about the size of our solar system today. So we're talking about huge, vast scales in a very, very short amount of time. And yeah, so we like to study this very, very brief earliest instant that we can look at, and we'll figure out how we can use observations today to tell us about this period. So the original motivation for inflation was some kind of classical problems in cosmology. I'm guessing everybody's somewhat familiar with those, but in a nutshell, inflation provides the flat, homogeneous, isotropic initial conditions for the subsequent evolution of the universe. So it kind of sets the stage for the evolution of the usual octave bang story that follows inflation. But it wasn't completely flat, homogeneous, and isotropic, but instead there are, very importantly, small quantum fluctuations that were generated during inflation, which produced density perturbations, which then sourced all of the structure that we see today. This would be more the focus of the talk. So the two main observables that we use to study inflation are the cosmic microwave background and large-scale structure. And so very quickly, the cosmic microwave background is the light that's left over from the period. It's sort of the earliest light that we can observe. That is, before the emission of the CMB, the universe was filled with a hot, dense plasma. Light couldn't travel very far, but at some temperature, electrons and protons were able to combine into hydrogen. The universe became transparent, and light has been traveling to us largely unimpeded ever since. And it's the differences in the temperature of that light at different points in the sky that we can use to really study the primordial features in that hot, dense plasma, specifically the density perturbations, and hopefully one day also tensor perturbations. And the other main tool for observation is large-scale structure. So those same density perturbations that led to temperature fluctuations in the CMB also lead to all of the structure, the matter structure in our universe. And large-scale structure is a useful tool to probe these initial conditions that we think are set by inflation. And to be a little bit more specific, what we are interested in is not the actual distribution. We don't predict from inflation what the large-scale structure, what the CMB will look like at one point. What we're interested in is the statistical properties. So the correlation functions present in the CMB temperature fluctuations and also in large-scale structure. And roughly speaking, what we do is we pick one point in the sky and there's some perturbation there. We specify an angle and ask how likely is it that there's another perturbation at that angle, and then average that over the whole sky. And we do that with 2, 3, 4, etc., any number of points. And that gives us the statistical information about large-scale structure in the CMB that we can hopefully connect to the earliest periods of our universe. So with that lightning review of inflation and how we actually probe it, let me now move on and talk about why it is that we think inflation has anything to do with those observational tools. And I'll be talking specifically about the conservation of correlation functions. This section will follow pretty closely a paper by Weinberg in 2008. So I'm going to be using his notation and links for his results in this section. So the overarching question is, why is it that we think inflation has anything to do with observations we make today, especially given that there's all sorts of physics that intervenes between inflation and kind of the hot Big Bang story that we understand at much lower energies. To be a little bit more specific, in this big blob of question marks here, we know that things like dark matter decoupling, electroweak symmetry breaking, perhaps supersymmetry breaking, reheating, all of that kind of stuff had to take place, and we don't really know how all that worked. We have some ideas how it may have worked, but we really don't have any way to probe that period. And we make measurements today, so why should we expect our measurements today have anything to do with this much earlier period, with this big intervening unknown era in between? Well, one thing that might help us is that all the wave numbers relevant for the cosmic microwave background and large-scale structure were far outside the horizon during this unknown era. And specifically what I mean by that, whenever I say outside the horizon for the remainder of this talk, what I mean is that for a given wave number k, divided by the Robertson-Walker scale factor a at some time t, is much less than the Hubble rate or the Hubble parameter at that same time t. So I'll just loosely refer to that as outside the horizon, but what I mean specifically is this. And so all of the modes that were relevant to the CMB and large-scale structure were far outside the horizon during this intervening era. Of course, there were modes that were still inside the horizon that were too small to observe, so we just won't concern ourselves with those small wave numbers. Just to make this a little bit more clear, what I mean is that during inflation, so this red line here is roughly the horizon side, so the sound horizon side is just the inverse of the Hubble rate. So the horizon size was roughly constant during inflation. At some point there was a transition to a radiation-dominated era, when this began increasing, and then it began increasing a little bit more slowly during a matter-dominated era. And this whole time, the wavelengths of any particular fluctuation, or any wavelength in the universe, is stretched along with the expansion of space. And so these green lines give you some examples of some particular wavelength that are being stretched with the expansion of space. And what I mean when I say a mode is outside the horizon is that its wavelength is larger than the Hubble rate at some time. And so during inflation, modes exit the horizon. They remain outside the horizon during this intervening era about which we don't know a whole lot. And at some later time, when we do understand of the physics of what's going on, these modes re-enter the horizon and provide the initial conditions for the subsequent evolution of the universe. Yes?
What do you find when you say the hot Big Bang explosion?
Oh, all I mean here is this dividing line here just means this is a temperature below which we understand the contents of the universe. So this, I can even take this to be as low as, say, like 10 MeV, when we certainly understand the contents of the universe. We're thinking baryons, cold dark matter, electrons, neutrinos, protons. All I mean by hot Big Bang expansion is it's the usual story that doesn't involve all this other stuff that we don't understand. So this is kind of standard radiation-dominated expansion. Okay. So the fact that these modes are outside the horizon is only useful if there's something that is conserved when those modes are outside the horizon. And luckily there is, and specifically, there always exist adiabatic solutions, so-called adiabatic solutions, in which the curvature perturbation, which I'll call zeta, and the gravitational wave amplitude gamma are conserved outside the horizon. So this is an old story, a very old story. It goes back to Martin in the 80s, and I'm sure there were others that I'm missing a lot of references here. But anyway, this is an old story that there are these so-called adiabatic modes, which always exist, in which these parameters zeta and gamma are conserved, and it's these things, zeta and gamma, that set the initial conditions that eventually give rise to fluctuations in CMD, large scale structure, etc. And to be a little bit more specific about what I mean by these adiabatic modes, in a particular choice of gauge, all metric fluctuations apart from zeta and gamma vanish, and all matter fluctuations also vanish in these adiabatic solutions. So the solution looks like just a regular unperturbed Robertson-Walker metric with unperturbed matter densities, except for zeta and gamma, which characterize the perturbations, the scalar and tensor perturbations in the metric. So I'm going to run through very quickly an argument that these adiabatic modes always exist, these adiabatic solutions always exist. So don't get too bogged down in these formulas. I'm giving you this basically just to show you the form of the solutions that I'm talking about. So the spatial part of the metric takes the form of, so this is the Robertson-Walker scale factor that will appear throughout here. If this were an unperturbed Robertson-Walker metric, this would be just a squared, this would be a delta ij here. But in the adiabatic solutions, what we have instead of a constant delta ij here, we have a matrix which is constant in time, but varies in space. This strict G is, this is really the thing that encodes all the information that deviates it from an unperturbed Robertson-Walker metric. And anywhere you see this kind of script, so for example, this Rij, this is the Ricci tensor constructed from this metric. And likewise, this is the Ricci scalar constructed from this metric. What we see is that the spatial part of the metric approaches a constant matrix, which has a spatial dependence, plus some other stuff where these F's are all of order a to the minus 2. And so specifically when a mode is far outside the horizon, when A is large, these are small corrections. Likewise, the same would be true for the G and H that are here down here. So what we can see is that this, the leading part of the space-time part of the metric vanishes for large A of T, G00 versus -1. And likewise, you can see for the matter part, so this is just the stress energy tensor, and this is any full scale quantity. So what we see is that we have basically a solution of the form that I was speaking about with corrections that are on the order of a to the minus 2, which become negligible far outside the horizon. So just a very quick argument that this solution does in fact exist. This is very similar to like a soft pion type argument for the existence of pseudo man-movers when it goes on. So the basic idea is that the field equations that govern the metric and matter fluctuations are generally covariant, but the solutions to those equations are not. So starting from the unperturbed Robertson-Walker solution and making a replacement of this Kronecker delta with this, again, constant matrix which varies in space, this thing is not a solution only because this is not a constant matrix. So therefore, the metric and matter equations will deviate from your unperturbed form only by derivatives of this Gij. Because in the limit where this actually becomes a constant, then those terms should vanish and we should get the unperturbed solution. And then the extra piece of information we need is that the powers of A that appear in the solution are fixed by invariance under a particular scale transformation of this form. And so putting these facts together, we get this type of solution where all of these functions are functions of A that scale is A to the minus. Okay. So this is all well and good. So these things exist. Adiabatic solutions exist. In the adiabatic solution, the relevant fluctuations are conserved. But this is only useful if this is the form of the solution in some particular physical situations that govern the early universe. And it turns out that there are at least two cases where the adiabatic solution is attractive. The first, and probably the most familiar to everyone, is single field inflation. So in single field inflation, what I mean by that, first of all, is just inflation driven by a single scalar field with no other dynamical degrees of freedom. And the other situation is local thermal equilibrium with no non-zero conserved line numbers. And here I just mean that the only relevant scalar fluctuation is the temperature fluctuation at any point in space. So in both of these cases, the adiabatic solution that I showed you in a couple slides back is attractive, and so we can guarantee that if either of these periods last a sufficiently long time, then the universe will be described by the adiabatic solution in which the curvature perturbation and the tensor fluctuation are constantly conserved on some horizon. However, this is not enough to conclude that the correlation functions are conserved. So we have, at this point, said that the classical variables will be conserved in the adiabatic solution, that the universe actually takes that form of the solution in particular in some physical situations, but that's not enough to guarantee the conservation of the quantum correlation functions. And so there are basically two complications that come up that prevent this from being an implication here. So the first is the issue of time-dependent constraints, and the second is the issue of loop graphs or loop correction. So I'm going to deal with these things in turn here. All right. Are there any questions at this point? Okay. So first of all, the way we calculate correlation functions in cosmology is not the same way that we calculate S-matrix elements in high-energy physics and particle physics. So in particle physics, what we do is we specify a state at some very early time, very far from the scattering center, and we ask what is the probability that we get some particular state, again, very far in the future, very far from the scattering center. That's not what we do in cosmology. Instead, what we do is we specify some initial state in the very distant past. In cosmology, we're not allowed to turn off the interaction, so we can only specify the initial state. So what we do is we specify the initial state and we ask what is the correlation of some particular quantity at some later time, some later fixed time t. Again, not the infinite past, but some fixed time t. And so this is called King formalism, also sometimes called the Schwinger-Keldysh formalism. And it's the method we use in cosmology to calculate correlation functions, specifically of curvature perturbations and tensor fluctuations at some specific time, late in inflation, which I'm going to call T1. So it's useful for what I'm going to be doing to define a generating functional in order to talk about all the correlation functions at the same time, rather than proving this case by case. And so this is kind of the usual story that you would normally do for particle physics, except instead of an in-out type of generating functional, we're going to have an in-in generating functional. And so this is just some mathematical object whose derivative is actually the correlation function. And the idea is that this quantity W, the generating functional, contains all of the information, contains information about all of the information about all of the correlation functions. So specifically, if I take 4 derivatives of this quantity and then set to 0 this external current J, then I get the sum of all of the graphs that contribute to the 4-point function, including both tree graphs and loop graphs. And so for now, what I'd like to do is focus exclusively on tree graphs, and I'll return to loop graphs in the next section. So in order to do that, I employ a trick, and this is kind of a standard trick that one of you.
Currents here?
I'm sorry?
What are the currents? I assume J is a current.
Yeah, it's an external current. It's just basically an auxiliary current to which these Qs couple. So this is rather abstract at this point.
Right.
But these Qs, you should have in mind that these Qs are the zetas or the gammas that I was using before. So this is the curvature perturbation. And the generating functional is a functional of this external current, which we end up setting to 0. But the basic idea is we would put in the source term for the zeta in this generating functional. And I'll actually be a little bit more explicit about it when I get to just a few slides ahead.
On the context of
Okay. Good. So, in order to look at just the tree-level generating functional, what I'll do is employ a trick, which is to introduce a fictitious coupling constant in front. So basically a loop counting parameter that I'll then set to 0. And the idea is you get just the tree-level contributions. And so So the tree level generating functional takes this form, where this is just the standard Lagrangian, and now those capital Q's that I was using, which are the Heisenberg picture operators, have been replaced by these small q's, which are ordinary complex functions q, which are subject to some constraints here. And so these constraints, well, here are the constraints first of all. The first is just that these q's, these complex functions q, obey the Euler-Lagrange equations. This is what specifies that the physical system we're talking about is actually modeling the system we want it to model. This just says that the q's obey the same equations of motion as the classical variables. We also have the constraint that these q's have to be real at the time t1 at which we evaluate the correlation function. That is, if these q's should describe some physical quantity, it should describe a real physical quantity as opposed to imaginary one. And then, so this is what the permanent actually is. This is here's the tree-level generating function. So it's some particular derivative of the Lagrangian with respect to the conjugate.
Okay, what's the one?
What's the Lagrangian? So let's see. Well, so
Show
Lagrangian.
us the Lagrange.
I will. Okay, yes. So I'm being very general right now. I'm sorry. Go ahead.
Is Q a physical quantity here?
I'm sorry.
Is Q a physical quantity here?
So Q, at this point, Q is just a C number function of time and space. That's all it is right now. I'm trying to be very general at this point. What the Q's will become are the zetas and gammas when we're talking about a specific cosmological world here.
Well, does it have to be real? Because like, like there, you just,
Actually,
oh well, I mean, for some cases, you always see like gaps to be valid. So it doesn't necessarily have to be real. Q itself doesn't have to be real.
well, so Q doesn't have to be real. Q at time t1 has to be real because we want, so zeta is just part of the metric. It's just a metric perturbation.
Okay, so Q is something that we can actually see.
Yes, at time t1, it should match on to the classical solution of the basic idea. Good. So yeah, sorry, this is rather abstract at the moment. We're going to do a couple of slides to go back to cosmology proper. The last constraint is some initial condition. And here I've chosen a specific initial condition. This in principle could be modified. This is just a positive frequency constraint. This is equivalent to specifying the so-called Lunch-Davies vacuum that we start with no fluctuations in the initial state. And this is just saying that all of our fluctuations, all of our fields Q starting with that. And that's all this is saying. But again, we could change this constraint in some different states. Okay, so the important point of this slide is that constraint 2 here, which specifies that Q is real at time t1, and also that the current is constant and real at, constant at time t1, gives an implicit time dependence on, implicit t1 dependence to these variables Q. So one important thing to do is we have to check that this implicit time dependence vanishes in the particular limit that we're interested in. So to summarize that, the requirements for the constancy of the generating functional in the limit of large A of t are, first of all, that the variables themselves have to approach a constant. So again, these things which are standing in the zetas have to approach a constant. So that derivative that appeared in that second constraint has to approach a constant. And furthermore, the integral that appears in the generating functional also has to approach a t1 independent constant in the limit of large A. So all I'm saying here is that the constraints themselves have to have, whatever time dependence they have has to vanish in the appropriate limit that we're interested in. Okay. Good. I should also mention before I move on here, so all of these conditions are in fact satisfied by single field inflation. And so this next section, what I'm going to look at is whether those constraints are satisfied by local field equilibrium. Are there any more questions at this point? Okay. All right, so here's the Lagrangian. So this is, again, pretty general. But the Lagrangian is basically just the Einstein-Hilbert part plus some data Lagrangian. And now part of the problem with local thermal equilibrium is we would like to be completely general and be able to study all systems that would be in thermal equilibrium. And so we don't want to pin ourselves down to any specific form of the matter Lagrangian. We don't want to specify matter content to make a very general statement about thermal equilibrium. And luckily, whenever the comoving entropy density is conserved, we can write the matter Lagrangian simply, sorry, I should say the on-shell matter Lagrangian simply as the pressure. And this is the same pressure that would appear in the perfect fluid form of the stress energy density. Now, the comoving entropy density is conserved in local thermal equilibrium, and so we're allowed to use this for the value of the Lagrangian in this particular case. So, in this case, what we find is that the generating functional, the integral that appears in the generating functional, takes this form. And so I'll come back and specify exactly what these quantities are. I'm also skipping a lot of steps here because it's a lot of algebra. But the basic idea is, in the particular form of the solution, which is attracted in local thermal equilibrium, this integral ends up taking this form after some integration by parts and other kind of manipulation. So what we need to do is check that this integral converges to a constant, a T1 independent constant at large in T. And so to do that, we need to check the explicit formula solutions for U, the momentum potential, and Gij, the metric. Okay, so as I showed you before, actually the solution for the metric in the adiabatic solution has a form that looks like this. So specifically, the real part of the time derivative of the metric goes as a to the minus 2. And the imaginary part of the metric scales as a to the minus 3. The momentum potential, so again, the momentum potential is just a fluctuation of the space-time part of the stress energy tensor. It has, in the adiabatic solution, it takes the form where its real part goes as a to the minus 2, its imaginary part goes as a to the minus 3. And so if we go back to this integral, what we see is that this combination, U times Gij dot, goes as the imaginary part of that goes as a to the minus 5, multiplied by a to the 3 gives us a to the minus 2. And over here we have an a to the minus 2, and the imaginary part of Gij goes as a to the minus 3, which cancels this factor, a to the minus 3. And so in the end, what we find is that the imaginary part of the Lagrangian, so this integral which appears in the generating functional, scales as a to the minus 2 in a limit of large A. And so what I've shown here is that the integral appearing in the generating functional approaches a T1 independent constant in a limit that A of T is large.
I was reading you explain this. The Lagrange density is the pressure.
Yes.
Can you derive Euler equations like that from such a formula?
Okay, good question.
I got stuck there kind of.
Yeah, good question. So that's why I made a point to say on shell here is because you have to, if you want to derive the Euler-Lagrange equations from this form of Lagrangian, you need to also give some thermodynamic quantities, thermodynamic equations which you cannot derive from this. So this gives the appropriate value of the Lagrangian, but this doesn't contain all the information you need to derive the equations of motion for whatever sits in this matter Lagrangian.
Okay, but why is it the pressure?
Why is it the pressure?
Yes. You referred to Schutz 1970, so
yes.
That's the basic reference in this. So
Yeah.
That's Bernie Schutz.
Yes. Yeah, I mean, roughly speaking, so one easy way to say it is for a scalar field, you can see that this is exactly what you get. For a scalar field, the pressure is given by the kinetic term minus the potential, which is just the Lagrangian you have for, yeah, so that's the kind of the standard scalar field Lagrangian, but this works more generally whenever you have a perfect fluid form for the energy. And yeah, it uses thermodynamic arguments. Like I said, you can actually derive the equations of motion from this without additionally specifying, for example, the second law of thermodynamics holds, which is why you have to assume that the coordinate density is conserved, for example.
Does this mean that the Lagrangian somewhere gets free energy.
It's possible that that's the case, yes. Okay, good. So we've shown that the integral appearing in the generating functional approach is a T1 independent constant in the limit of large A. And there's a similar argument, which I won't go through the details of, but that second constraint, that the derivative appearing in that second constraint also approaches a time independent constant, T1 independent constant in the limit of large A. And so as a result, we can conclude that in the tree level generating functional, and therefore all of the correlation functions derived from it are constant outside the horizon during and following local thermal equilibrium with no non-zero concern quantity. Okay, so at this point we've shown that all of the tree level correlation functions approach a constant in the limit of large A. And what I mean specifically by the limit of large A is when these modes are far outside the horizon. So you might ask, A is large compared to what? Well, it's large compared to A over H. All right. So we've taken care of the tree level case, and now we'll move on to loop corrections. And loop corrections, what I mean by loop corrections, by the way, are just the same thing you would mean in particle physics. It's the loops that appear in Feynman graphs. These really aren't Feynman graphs. I shouldn't say Feynman graphs here, but in this diagrammatic formalism, these loops kind of enter in the same sort of way. Loop graphs, the issue that they bring up is that they inevitably contain integrals over wave numbers which cannot be restricted to the outside the horizon. So a loop graph like this contributes from all ranges of so I'll use Q for the internal wave numbers. So this graph gets contributions from all values of Q, including those which are not outside the horizon, those for which Q over A is not less than H. So as a result, so what I should emphasize here is we can't rely on the assumption, or we can't rely on the fact that the solution is adiabatic, because this graph receives contributions from internal wave numbers which are not outside the horizon, at which point the variables are not constant, even in the adiabatic solution. All right. So I should point out right up front that these loop graphs typically are not going to be very relevant for observation because loop graphs are typically much smaller than the tree level graphs. And to be a little bit specific, graphs containing L loops are suppressed by this loop counting parameter here, which is the Newtonian G and times the Hubble parameter squared. And we know from the non-observation of tensor modes that this quantity here is something like 10 to the minus 10 or even smaller than that. And so these corrections are extremely small in terms of observation. So you might ask, why do we care? Why am I bothering to look at them at all? Well, if they do contain a time dependence, that is, first of all, I should say that it's important to understand the theory we're working with to all orders of perturbation theory, even if it doesn't necessarily have observational consequences. If we're really claiming that we're generating quantum mechanical correlation functions from inflation, we should really understand all that implies. And second of all, if there is a time dependence in these graphs, even if it's small, that tells us something that we can't rely on the absolute conservation of these correlation functions outside the horizon due to the presence of these quantum corrections. So it was proven by Weinberg that these graphs are never proportional to positive powers of the scale factor, though they may contain factors of the log of the scale factor. So again, even if they contain factors of the log of the scale factor, you would need huge numbers of e-foldings of inflation in order for these to become relevant. On the other hand, there are models of inflation, so-called eternal inflation, where you have arbitrarily large numbers of e-foldings of inflation, where these things could in fact have an impact on physical observables. And so that's one motivation at least for looking at these graphs. Yeah, so, okay. So I should say at this point, I'm not claiming that these actually do contain powers of log A. All I'm saying is that it's been proven that they don't contain positive powers of A, though they may contain powers of log A. So what I'm going to try to answer in this section is whether these log A terms actually appear. I won't be able to answer that question, unfortunately. But the issue at hand is to calculate whether log A terms do in fact appear. But roughly speaking, if they appear, it's because you're getting contributions from a longer history of inflation where these with the momentum loops that could contribute to.
It comes from the cutoff of the integration.
I'm sorry.
So it comes from the cutoff of the integration.
Yes, right. Yeah, this is an IR effect, really. It comes from, low limits or other time. All right, so the problem, or one problem with calculating these things, is that all these calculations are complicated by the presence of ultraviolet divergences that naturally appear in the calculated using graphs. And the problem is pretty bad in gravity. You naturally get quartic, quadratic, and logarithmic divergences, all of which appear for any one graph. We need to regulate these divergences in order to extract a finite part that may or may not be time dependent. And the regularization scheme we use had better not violate general covariance. After all, general covariance is just a mathematical implementation of the principle of equivalence, and so this physical regulator scheme had better not spoil the equivalence principle. So past studies of this problem have relied on dimensional regularization, which is generally covariant, but it has some problems. Specifically, if you don't know the analytic form of the wave function, dimensional regularization is very difficult to employ because what you need to do is analytically continue your solutions from an arbitrary number of dimensions. And if you only have numerical solutions, you can't do that very easily. Furthermore, when dimensional regularization has been employed in cases like slow roll inflation or pure de Sitter expansion, people have arrived at different results. People have disagreed specifically about whether factors of log A appear in these loop directions. So it might be nice to have another way to approach this problem. And one other way to approach it is Pauli-Villars regularization. So Pauli-Villars has a long history, goes back to 1949, when Pauli-Villars introduced it as a way to regulate divergences in QED. So the basic idea of the scheme is wherever you see a propagator, which typically scales as 1 over q squared, you replace that with 1 over q squared minus 1 over q squared minus n squared. The idea being at large q, this n is irrelevant, and so these things cancel. At very low q, the n dominates, and for very large n, this whole thing is negligible, and so you just restore the usual propagator. Of course, we can't just go in by hand and replace these things and hope to preserve general covariance. So what we need to do is find a way of introducing fields that reproduces this type of behavior. And so what we end up doing is putting in fictitious Pauli-Villars regulator fields into the theory that give us the behavior that I was just discussing. So I'm not the first to use Pauli-Villars regularization in gravity. So specifically, people have looked at applying Pauli-Villars regularization in fixed curved or expanding backgrounds. But there are some additional problems that arise when gravity is dynamical. And specifically in inflation, it's necessary that gravity is dynamical. The curvature perturbation zeta is a mixture of the metric fluctuation and whatever scalar field happens to be around during inflation. And so we need to work with a dynamical metric in order to really capture all of the physics that's going on during inflation. And so to be a little bit more specific, if we just try to apply Pauli-Villars as we would expect to do, where we introduce some regulator fields, then things go wrong. So let me go through that argument. So if the Lagrangian contains some number of Pauli-Villars regulator fields with some maxes, and we put in the wave function normalization we can expect to do, what we find is that each propagator scales as 1 over this wave function normalization. And so let me just pause here really quickly. For QED, what you would do is just put in a minus sign. For this is theta, or sorry, this is E would just be -1. And so for each regulator propagator, it appears to the opposite side of the physical propagator, so you're able to cancel the divergences. The problem in gravity, however, is that if I put in this z, then my vertices are also proportional to the factor of z. And so if I put in, so as a result, in all of the one-loop graphs, the number of vertices is equal to the number of regulator propagators. And so the factors of z always cancel out. And so any one-loop graph I write down will never contain any factors of this z. So regardless of my choice of z, I can never regulate divergences with this set of regulator inputs. Okay. But all is not lost. Instead of using just regular old regulator fields, we can add anti-commuting scalar regulator fields. And so these are graphs mean variables where they switch their places at a -1. And just like usual fermions that appear in loops, you get an additional minus sign whenever you have a loop, a fermion loop or an anti-commuting field that runs on a loop. And so if we add additionally these anti-commuting scalar regulators, what we get is whenever we have a particular graph, we have the loop that contains the physical fields, which contributes the number of physical fields running in the loop, plus the number of commuting scalar regulators that runs in the loop, minus 2 times the number of anti-commuting regulators that runs in the loop. And so if we appropriately choose the number of regulators and also the masses, and I'm not really talking about the masses here so much, then we can regulate all the divergences. So I've shown here how the probability of divergence can get regulated with the same thing.
So to what extent is this translated into, general stability or gravity? This particular context?
Yeah, so there is a drawback.
Are you turning gravity into supergravity here, or?
No, I'm not. So yeah, this looks very supersymmetric, right? That I'm using these anti-commuting. This is the same trick that supersymmetry uses to cancel its divergences, which is that for every scalar, for every bosonic degree of freedom, there's a fermionic degree of freedom in order to cancel divergences in the same sort of way. I'm really not using fermions here. I'm using completely unphysical anti-commuting scalars. So they violate spinning statistics. And so these are just purely a device in order to cancel divergences. So I'm not really making this theory supersymmetric. And so all the external fields are just the standard external fields that you would get in gravity. So these solid lines might be gravitons, or they might be factors of zeta that appear. There is a bit of a drawback in this method, which is it's still unclear how you would regulate divergences that come from internal graviton lines. And I don't have a solid answer.
Is that the essence of Kalman normalizing general relativity, or?
It's very much related, yes. Yeah, it's strongly related to that. So this method will work for regulating the types of divergences that come up in inflation, in calculating loop corrections in inflation. And it will hopefully be able to answer the question of whether log A terms appear. Unfortunately, that calculation isn't quite done yet, so I can't give you the final answer. But this is a scheme which gives an alternative to dimensional regularization, which should be used to, or which can be used to check the results. All right. I see that I'm kind of running out of time here. Are there any questions at this point? I'm going to kind of switch gears. Okay. I'll kind of go through this last bit quickly because I can see I'm running out of time. This last bit, I'm going to now take the lessons that we learned in the first part of the talk, which is that correlation functions are indeed conserved outside the horizon when we're in the adiabatic solution, and we're going to apply that to multi-field inflation, a specific class of models of multi-field inflation, and look at how the role of adiabaticity affects specifically non-Gaussian intervals. This is based on a pair of papers that I wrote with a postdoc. He was in Texas and now in Cape Town, South Africa. So inflation has passed a bunch of observational tests. It's very successful at reproducing the power spectrum that we observed in the cosmic background, for example, which gives us a lot of faith that something like inflation or something very close to it happened in our early universe. We think we've got to the point where data has begun to rule out some of the simplest models of inflation. So this is a plot from the leveling out team of the tensor to scalar ratio versus the spectral tilt. And we can see that some of these models we can be pushed outside the allowed region of strand shaded regions. But there's still a whole slew of models that remain within the observationally allowed region. And so we'd like to have another tool to discriminate between different models of inflation. So one of those tools that shows a lot of promise is Non-Gaussianity. And Non-Gaussianity just refers to all the higher point functions of correlation functions. And so it may be a very good tool for constraining models of inflation, models of the early universe. In principle, it contains a lot more information. The power spectrum is essentially a function of a single, it's essentially two numbers, if you parameterize it in terms of just the amplitude and the tilt. Non-Gaussianity contains, is a whole function of these ratios of wave numbers. So there's a lot more information in Non-Gaussianity in principle if we can insert it. So Non-Gaussianity has already been constrained to some degree by the map. And specifically, the three-point function in two forms has been constrained. There's actually another form that's constrained too, which I have listed up here called the orthogonal shape, which is hard to draw in terms of these triangles. But the local shape will be of particular importance to us. This is its main contribution for these so-called squeeze triangles, where one element is much less than the other two. And future experiments, including quantum and large-scale structure, will do a lot better at constraining Non-Gaussianity. So the forecast for quantum is something like the error will be reduced to about 5 on FNO local. Projections for large-scale structure should push this down to about 1 or some degree, so maybe about 120. That's probably the obvious. So within just a year, we'll have much better data on FNO local. And FNL local is of particular importance because it, due to something called the single field consistency relation, FNL local is small in all models of single field inflation. There are probably some caveats I should add here. If you modify the initial state in some particular ways, I think you can do any of this. But at the very least, FNL local is small in a very wide class of single field inflationary models. So convincing detection of FNL local would rule out, I would say, almost all models of single field inflation. And the reason that single field is treated differently from multiple field inflation goes back to this issue of adiabatic solutions. So multiple field models of inflation naturally produce non-adiabatic fluctuations, and it's only in the adiabatic solution that the curvature perturbation and its correlation functions are conserved outside the horizon. So in multiple field inflation, due to the presence of non-adiabatic fluctuations, correlation functions can evolve on superhorizon scales. So what you get at horizon exit in single field inflation is what you have at the end of inflation, but that's not the case for multiple field inflation. And so in multiple field inflation, the idea is you could start with Gaussian fluctuations at horizon exit, but then evolve in a particular way to produce large local non-Gaussianity. However, non-adiabatic fluctuations which persist through the end of inflation, which persist up to the radiation-dominated era, leave observable effects in the CMB. And so I have over here just the power spectra for various forms of isocurvature, so-called isocurvature or non-adiabatic fluctuations. And you can see that you can distinguish these. And WMAP has already put constraints on some forms of non-adiabatic fluctuations. So there's no hint in the data of any non-adiabatic fluctuations which are present in the radiation-dominated era, at least at this point. And so that leaves us in a funny position where we have the possibility that multiple field inflation might produce large non-Gaussianity, but it also naturally produces non-adiabatic fluctuations, which we don't detect in the data. However, non-adiabatic fluctuations need not remain throughout the whole period of inflation or throughout the whole period until radiation-dominated era. And like we discussed earlier, there are at least two ways in which non-adiabatic fluctuations can become adiabatic. The first is effectively single field inflation. And what I mean here by effectively single field inflation is that all of the masses of the scalar fields, except for one, become large for some period of time during inflation. So in other words, the inflaton rolls through a steep valley in field space. And the other possibility is local perpendicularities. That was the second section of the talk. And so the main point I'd like to make here is that non-adiabatic fluctuations allow the correlation functions to continue to evolve outside the horizon. So to really make predictions from a multiple field model of inflation, we need to understand the evolution all the way up until the time when the fluctuations become adiabatic, because it's only at that point when they will be conserved thenceforth. So in order to understand really what this model is saying, we need to understand the evolution all the way up until the time when the fluctuations become conserved. So the question I'd like to ask is whether there exist models of multiple field inflation which predict both a large FNL local, large local form non-Gaussianity, and a purely adiabatic power spectrum. That is, can you generate a large local non-Gaussianity and then force the solution into an adiabatic one such that that's guaranteed to be conserved and be consistent with the non-observation of non-adiabatic fluctuations in the CMD. And so what Now and I did was study a particular class of two field inflation models which passed through a short phase of effectively single field inflation sometime before the end of inflation in order to force the fluctuations to become adiabatic. And therefore, we don't need to specify a model of reheating. We don't need to talk about what happens after inflation. We can make distinct predictions. And so the class of models we studied took this particular form. So potential is a function of a sum of scalar functions of the two fields. So this is a pretty wide class of potentials. It doesn't include everything, but it includes a pretty wide class of potentials. And then more mechanically, we use the so-called delta N formalism to calculate FNL local after passing through a steep valley. And what we find is that as the inflaton rolls through a steep valley, which is characterized by this eta SS parameter being larger than 1, what we find is that the entropy perturbations, the perturbations perpendicular to the direction, or I should say the non-adiabatic perturbations, scale as e to the minus 3 halves times the integral of h. And meanwhile, FNL local has some terms which are suppressed by slow roll parameters, plus something which appears to get large as the inflaton rolls through a steep valley, but then which becomes exponentially damped as the inflaton continues to roll. And what you can see is this is always damped more quickly than the entropy perturbation. And so as the solution becomes adiabatic, it also approaches Gaussian. Well, I shouldn't say that. It also approaches a slow roll suppressed value of the FNL local. It turns out you can go through the same sort of argument for the higher point functions. And for the 4-point function, what you see is tau NL and GNL, which characterize quadraticals that look something like this in limited space. These things also become slow roll suppressed. And in fact, you can make a general argument that all local form endpoint statistics approach slow roll suppressed values after passing through a steep valley in field space.
On the convergence, did you assume slow roll conditions for both fields?
Yes. We discussed a little bit violations of slow roll. If the violations of slow roll are small or short, I should say, you really don't expect to change these results too much. There's also some numerical studies where this qualitative behavior remains true that violates slow roll. So even in the cases where you violate slow roll, this seems to no our proof does not show that. I should also say there's some caveats. These so what I've written is strictly true, but these terms which are suppressed by slow roll parameters aren't always particularly small. There are other factors that enter in which can make these things large, though not arbitrarily large. But it still might be in the observational interesting range.
So what is adding an extra field that you take?
So having an extra, so if you have an extra field, then, roughly speaking, so in this diagram, what I'm trying to show, this is a non-adiabatic fluctuation, kind of very schematically. An adiabatic fluctuation, if you had multiple fields, all of the fields would be perturbed in the same way. There's essentially one scalar degree of freedom which controls fluctuations to all fields. A relative perturbation between two different fields is a non-adiabatic fluctuation. And so with two fields, in addition to having them both perturbed in the same way, you can have a relative perturbation between the two fields, which means that, in that point in space, there's a different history than another point in space. Another way to think about it is
You have something parameters in essence.
yes, exactly. Yes. All right. So yeah. So the conclusion is all of these local form endpoint functions are slowly suppressed after passing through a steep valley in field space. And let me go ahead and summarize. So first of all, cosmological correlation functions are conserved outside the horizon following single field inflation or local thermal and chemical equilibrium in the tree approximation. Loop corrections require careful treatment due to ultraviolet divergences. I dealt with the way I showed you a way to deal with these ultraviolet divergences using Pauli-Villars Regularization. And out of their way, they're probably irrelevant for observation, even in the cases where you have many equal loops. But it's an important thing to check nonetheless. And lastly, the approach to adiabaticity during multiple fluid inflation leads to small suppression of local form non-Gaussianities. That's it. Thanks.
Maybe one or two more questions.
So with R and the slope of the tensors, remember there's this consistency relation that there's a kind of a bound if you have reasonable one-loop corrections, that if you couldn't, for any R you could hope to observe, you couldn't observe a slope. I was wondering if you thought about ways that you might be able to give detectable tensor slopes. I think this was single field. There's no way you could the regulation didn't permit.
So are you asking about so the consensus relation I know for which holds for tensors is that the actual slope of the tensor. So instead of the spectral tilt for the scalars here, if you look at the spectral tilt of the tensors.
Exactly. Yeah.
Yeah. Yeah, and there's a consistent relation between that and the amplitude of the tensors. So there are these ideas that you can generate a tensor signal which doesn't come from vacuum fluctuations. Presumably that would not obey the tensor consistency relation. So specifically, they look at cases where you have multiple fields, but you have one dynamical field, and then at certain intervals along the inclined trajectory, a different field direction becomes massless. So you produce a bunch of these extra massless degrees of freedom, which can then in turn generate tensors. And those, you have no reason to expect that they would obey this consistency.
So that's the best bet for getting some detectable departure.
Yeah, probably. I don't know of any others. Yeah, with vacuum fluctuations, you're really kind of stuck because what the consistent relation comes from is the fact that the tensor amplitude is just proportional to the Hubble rate, and or to put it another way, it's proportional to the scalar potential. And so the scalar potential sets both the amplitude and the tilt, because as it changes, that's what gives you the tilt. So you really need another source of gravitational waves in order to modify that.
Maybe we can go upstairs for cookies, and Joel is going to be around until Saturday morning, and as I said, we'll be running